So welcome to part 2 of lecture 4. I just finished off doing this example right here where I took F2 and I decomposed it as a direct sum of vectors of the form u and w. And let me just scroll back here so you can see what the u and the w were. The u was all the ones where the first coordinate is given and the second coordinate is 0, and the w is where the first coordinate is 0 and the y could be anything. And in fact, there's nothing special about this particular example that I wrote in red. If you take V to be any Fn, and if I take Uj to be the set of all vectors where every coordinate is 0 except for the vector in the j spot, okay, then what we have is the decomposition of Fn into the direct sums as follows. Okay, so we're just kind of that should be an n. We're just specializing the example that we did, right, just before the break. So what are we going to be doing kind of in this part is we're going to just be looking at ways to check whether something is a direct sum, check to whether something is a direct sum. So we know when we have to check whether something is a direct sum, we would have to check that every time I look in something in u1 up to um, the sum, that I can only write it uniquely in one way. Now that seems like a lot of work to do, right? Because there's an infinite number of things here. So the beauty of this little theorem here is saying that, well, you have a direct sum if and only if the only way to write 0 as a sum is write 0 as u1 up to um is when u1 is equal to u2 up to um is equal to 0. Okay, so just want to stress here is what's happening is in order to check whether you have a direct sum, you just need to show that you can write 0 uniquely. Need to only show that you can write 0 uniquely. Okay, and this kind of goes back to the very first example that I had when we started our lecture. Right here is I have this u1 and u2, and I have 0, and I've written 0 in 2 different ways. And so since I've written 0 in 2 different ways, I know I can't have a direct sum. Okay, and so the power of this is now, instead of checking over all possible u's, we just have to look at the 0 and see if we can decompose it in a particularly nice way. Well, first of all, let's kind of walk through our proof. So it's an if and only if statement again. So there's 2 directions. So first of all, we're going to assume that we're given a direct sum. And then we want to show that you can only write 0 in one way, right? And that direction is actually pretty clear because that's part of the definition of a direct sum, all right? Because then 0 is equal to 0 plus 0 up to, I'm not sure why that showed up there. Let me get rid of that. Up to 0, right, with each 0 inside of ui, and this is the only way to express it. Right, and it's the only way to express it is because we're already given that we have a direct sum. So 0 can be written as a sum of elements, each element coming from our ui. Once we have it, this is the only way we can do it. Okay, so one direction going from if it's a direct sum to this direction is quite straightforward. Okay, but it's the other direction that takes a little bit more work. So let's, I have a lot of room here to work out the details. Okay, and the proof is going to be saying like, okay, let's take 2 different ways of writing an element and we'll show that they have to be the same. Right? And so in particular, let's say I take a vector in the sum, and now suppose that we have that W can be written as A1 up to AM, and W can be written as B1 up to B2 up to BM, with each AI and BI inside of UI. Okay. And now we're going to do kind of one of a mathematician's favorite tricks is to write 0 in a special way, right? So 0 is the same thing as taking the vector W minus W. right? But now we can now substitute one way of writing W using the A's. And then we can take another way of writing W, which is the B's. And let me put a negative sign here, not a plus sign. So B up to BM. And now we're using the axioms of a vector space. We can regroup things. So let's take A1 minus B1 plus A2 minus B2 up to AM minus BM. Now each of these AI, like A1, B1 is in U1, A2, B2 is in U2, and so on. So we have, since each AI minus BI is in UI, the condition on 0, like our hypotheses, i.e. our hypothesis implies each AI minus BI is equal to 0. So another way of saying that is AI is equal to BI. Right, just let me reinforce why this is true, because we've taken 0 and we've written it as a sum of elements, where this element is in U1, this element is in U2, and so on. But our hypothesis implies that when you can write 0 in that way, then each of those pieces had to have been 0. Okay, and so what this means is that each of A1 is equal to B1, A2 is equal to B2, so there's only one way to write W. So there is a unique way to express the vector W. So U1 up to UM is a direct sum. Okay, so we've proved that theorem, and as I said, it's a very handy result to check whether something's a direct sum. You can just focus in on the 0 element. Okay, and just as a pointer here is we've done it for all, like as many vector spaces as we want, or subspaces, but when you have two subspaces, there's an alternative way to check. And basically what the theorem says is if U and B W are subspaces of V, then U direct sum, U plus W is a direct sum if and only if the intersection of those two spaces is 0. So let me just quickly run through the proof for that, because again, it's not that hard to do. Okay, so if we take something that's in the intersection, so what we want to do is assume that we have a direct sum, and we want to show that everything in the intersection is 0. But if we take W that's inside the intersection, then we know that 0 is equal to W plus negative W. Again, we're doing our trick of writing 0 in a special way. And we know that W is in U, and the inverse of W has to be in W. And here we're using the vector space property. Because W is in capital W, so is its inverse, right? But since U direct sum W is a direct sum, right? This implies that W has to be equal to negative W, which is equal to 0. So everything in the intersection has to be the 0 element. So that shows one direction. And now let's show the reverse direction. Okay, so let's take a vector 0. And let's say the vector 0 can be written as U plus W, with U inside of little u inside of capital U and W inside of W. And what we want to do is basically show, using our previous result, that U and W are both 0. Okay, well, from this information, we get that U is equal to negative W. Since U is inside of U, we have negative U, which is equal to the negative of negative W, which is equal to W is inside of U. So we have that W is inside U and it's inside of W, right? because W is in W, and we showed that W is in U, and we're given that this is equal to 0, right? So W is equal to 0, and thus U is equal to 0. So 0 equals 0, 0 equals 0 plus 0 is the only way to express 0, okay, and thus U direct sum, or U plus W is a direct sum. Okay, so this is just giving us a handy little trick when you have two subspaces to check whether it's a direct sum. So we'll pause here, and when we'll come back, we'll still do some linear algebra, but we'll focus on how to write proofs.